Scenario 1 Groundwater Flow Simulation. Overview. Effective management of subsurface contamination requires a clear understanding of groundwater flow, identifying contaminant-impacted areas, and evaluating appropriate remediation strategies. The software offers 3 pre-designed scenarios to support this process, each addressing a key contamination assessment and remediation stage. These scenarios are integrated into a template module designed for rapid assessment, with simplified model settings to make the setup process more efficient and user-friendly. Scenario Template Introduction. Scenario Template 1, Groundwater Flow Simulation helps users analyze changes in groundwater flow patterns, an essential step, as flow dynamics directly influence how contaminants are transported. Scenario Template 2, Contaminant Transport. Chlorinated solvent simulates key transport processes such as advection, dispersion, diffusion, and adsorption, supporting risk assessment and identification of affected areas. Scenario Template 3, Contamination Remediation. Bioremediation explores the use of lactic acid as a remediation agent, enabling users to evaluate its effectiveness under realistic subsurface conditions. Step-by-step operation. This video focuses on Scenario Template 1, Groundwater Flow Simulation. We can click the SCN01 item for detailed information about this problem. This simplified scenario is designed to help users understand basic groundwater flow dynamics. The model represents a 2D horizontal cross-section at a selected depth, covering an area 100 meters long and 50 meters wide. The geometry assumes a homogeneous material with constant properties. Boundary conditions are set using a constant water table elevation, 2 meters on the left side, upstream, and 1 meter on the right side, downstream. This creates a pressure gradient that drives groundwater flow from left to right. After running the simulation, the results display the velocity distribution, represented by color gradients and arrows indicating flow direction, and pressure head variations across the entire domain. Next, select Load to open the Scenario 01 template. Then we will see the simulation interface for setting up this scenario. Left panel, Model Setup. Follow the steps in sequence, Step 1, Step 2, and Step 3. This is the main configuration area where we define the model inputs step by step. This area contains all input parameters. Starting from the top, we define the project template and model type, followed by the geometry dimensions and mesh settings. Below that, we configure material properties, then set boundary conditions, and finally define the total simulation time. Right display area, output visualization. The top message box displays the operation status, helping us track each step of our project execution. The simulation results appear. We can switch between tabs, geometry, animation, and view. The support tools are designed to help pause, play, and jump across time steps. Confirm and enter custom X, Y, Z locations. Zoomed in and out, viewed from standard X, Y, Z orientations, saved as images, or copied for use in reports. Next, we'll set up the geometry for Scenario 01. This example simulates groundwater flow in a 2D environment. Begin by setting the simulation area to a length of 100 meters and a width of 50 meters. We can choose the model setup options, the conceptual, which uses a schematic layout. Next, define the source, monitor, and view points using offset fields that align with the visual panel values. The source point introduces water or contaminants into the system, the monitor point tracks simulation outputs at a specific location, and the viewpoint determines the section of the model displayed in the output panel. In this example, the view window is set at 70 meters in length and 25 meters in width. Followed by the mesh setup. Go to the mesh settings. The mesh refers to the grid of cells used to divide the model area for numerical simulation. It is foundational to how the software calculates groundwater flow and other processes across space. We can select from several mesh density options: very coarse, coarse, moderate, fine, very fine, or custom. Mesh density can be adjusted to control the level of detail in the simulation grid. A higher mesh density uses more, smaller cells, which increases accuracy but also demands more time and computing resources. In contrast, a lower mesh density speeds up the simulation but may miss finer flow details or local variations. In this case, we can select the moderate option and set the density to 1, which provides a balanced resolution suitable for most scenarios. Then, we'll define the parameters. Begin by setting the material properties for the hydrogeological layer. Although the simulation incorporates numerous parameters, only 3 are designated for user input due to their critical influence on water flow behavior. The interface primarily provides input options for porosity, hydraulic conductivity, and bulk density. All other parameters are maintained at default values derived from standard conditions to ensure consistency and accuracy in the simulation. This scenario 01 chooses sand as the material, with a porosity of 0.35, a 0.002 meters per second hydraulic conductivity, and a 1.895 gram per centimeter cubic density. Next, the scenario conditions are defined by setting the water table elevations. Input 2 meters for the upstream and 1 meter for the downstream sides. This creates a hydraulic gradient that drives groundwater flow from left to right. Lastly, set the simulation time to 150 days. This determines the total duration over which the groundwater movement will be simulated. Finally, we'll choose the output method. Now, click Execute and wait for the model to run. The top message box helps us monitor each step of the execution. When the message simulation process completed appears, the simulation has finished successfully. Next, we can check the output results. In the Variable Display section, we can view all results or filter by variables such as velocity or pressure head. First, we'll see the geometry results based on the view window we set earlier. Next, go to Animation and click Play to visualize how velocity and pressure head change over time. In the plane view, arrows show the flow direction, while color gradients represent water elevation. Finally, under the View section, we can check the velocity and pressure results at the observation point. All simulation results are fully interactive and can be zoomed in or out to examine specific areas in detail. Users can rotate the 3D view to standard X, Y, and Z orientations for better spatial understanding of the model output. Additionally, visualizations can be saved as image files or directly copied into reports. Thank you for your watching.